Welcome back, everybody, to the tutorial. It's my great pleasure to introduce Dr. Aleksandra Faust. She's an amazing speaker. She co-founded the RL research team at Google Brain. Before that, she works in the robotic team at Google, and before that at Waymo. She won IEEE Early Career Award, Best Paper Award at ICML, many other conferences, Best Dissertation Award. She recently wrote a brilliant survey on RL, which we'll talk about today. And before that, also worked on very interesting topics such as learning environments for zero-shot RL and many other things. So that's, I'm very much looking forward to this talk. And the floor is yours.
Thanks so much for the introduction. Is this too loud? No. Thanks for the introduction. And I'm going to be also want to introduce Ying J. Miao and Richard Song, who's going to do parts of the presentation with me today. All right. And thank you guys for coming. It's an amazing conference. It's really exciting to see it happen and so on. So my story a little bit about into AutoRL and learning comes from when I was doing PhD and doing applied reinforcement learning and trying to make things work, and the thing just wouldn't train. And then you try this and try that and experiment and you try different reward and so on. And I was like, okay, I'm tired of this. Let's just automate myself out of the work process. So that's the backstory. So for today, we'll go in basically roughly 4 sections. First, do some very basic introduction to reinforcement learning. And kind of go, why is it and how is it different than supervised learning? Then introduce AutoRL, what it is, what's some taxonomy of the problems and so on, what are different things we can learn. Very briefly introduce different methods we can use for learning, and then go in introducing what's actually being done currently in the field. And the idea here is not to give you a comprehensive overview, but to kind of give you a flavor of what's out there, and then we can end with what are the open problems and so on. So hopefully by the time we're done, and we're going to introduce also some tools. So hopefully by the end of the tutorial session, you'll know kind of how to approach the problems, what's solved. So if you're faced with applied problems, like, yeah, don't reinvent the wheel, just go and do it. But then if you're a new PhD or you're looking for new research, you're like, well, this is promising and open. So that's kind of the promise. Before we start, I'm curious, raise your hand if you consider yourself reinforcement learning expert. You're working in the field, you know what it is, and so on. All right. Raise your hand if you consider yourself comfortable with RL. Okay, about half of the room. And then consider yourselves like, I've heard this is a thing, but I really have no idea. All right, sounds good. It's a fairly small audience. Feel free to stop me, ask questions. Let's make this interactive and so on. All right, so let's start with reinforcement learning. Biological systems tend to learn from interacting with the environment. Let's see. Okay. And this is my 1-year-old daughter interacting with the environment, learning how to walk, right? And then eventually with lots of repetitions and so on, we kind of get to walking safely. In a similar way, there is lots of real applications in the systems where autonomous systems can help with all kinds of driving, robotics, right? Where systems are making decisions and controlling an interacting environment to perform some tasks for the user, sometimes in parallel with the user, sometimes fully autonomous. And this is the idea with the share autonomy versus the full autonomy. Other examples are, so some of these are embodied, or the loon, for example, and so on. Some are non-embodied planning and decision problems, such as protein folding, how we can kind of predict the sequence of motion that the protein does, or like navigating in different web crawlers that are really mobile manipulation tasks without embodiment behind. So there are lots of applications where this is applicable. Now, what are the methods? In a broad terms, what's reinforcement learning? It is a method for learning good decisions. So the setting is sequential decision making, which means you have an agent, have a robot or bot or kind of piece of software that interacts with the environment. It performs an action on it, reserves some numerical reward, and so on. And it's trying to optimize long-term benefit of it. And this is what we kind of call the return. It's formally formulated as partial observable Markov decision process, which is a fancy way of saying it's a tuple that has states, like what is the current state of the system, and that's often hidden. What are the actions that the system can perform? So for example, I can take a step now. The P is transition function that says if I have state now, I have an action, what is the next thing that is going to happen? The next one is reward. It's a scalar that depending, it maps states and actions into a scalar. So what happens if I, in current state, make an action, what is the scalar reward? There are different ways to specify it, either as a probability distribution or just a function of state and action and so on. Then we have omega, or O are observations. So hidden state is what is the kind of hidden state of the entire system. Observation is what the system can see or sense at the time. For example, in robotics, it might be just the image or so on. The different systems have different observations. And then big omega is the mapping that makes observations to states. And then we have terminal states, actually starting states, terminal states, and gamma. So that's the tuple. This is the formal setting for RL. The solution is a policy. It is mapping or a function that takes observation or a state and then returns an action or action distribution and so on. And we're after learning this policy term. And which policy out of all the policies that are parameterized with some theta, we're looking for the one that maximizes cumulative reward that the agent sees. Gamma here is called a discount factor. Discount factor is a constant that's smaller than 1 and kind of tells how long-term or short-term the agent is. So am I going to prioritize short-term rewards, or my payout's going to be in 10 years and so on. So that is the general setting. And then we have the agent that's training, so performs the actions in the training environment, receives observations, and here we go. So that's the very basic. So what are major components of the reinforcement learning? One thing that would be nice to do is have an estimator, what is my expected return? And often that's formalized as a value function. There are 2 of them, Q function and V function, that basically do an estimate of, okay, I'm in a state, and if I perform the action, what my return might be. And we can then learn either Q functions or V function or policy, they're connected. We have a choice what to learn. One thing that's very important for reinforcement learning agents is that in order to learn, agents need to explore. And there is a risk associated with the exploring, and there is this trade-off always as how much one explores and how much it exploits. So these are some basic terms. You can learn more in other places. But the point is, in terms of the algorithms, there is a choice what to learn. We can learn the model of reward or parameters. We can learn Q function, V function, or we can learn policy, or we can do both of them, and different algorithms do different ways. So from there, this is the zoo of the algorithms precisely that kind of comes out of these decisions. beyond the different either policy optimizations and so on, the algorithms and so on, you'll often hear terms off policy, on policy, and offline RL. On policy means that the same policy that we're training on, we're using to collect the new data and update. Off policy means that I have one policy that is being used to collect the data and the other one that I'm updating, and maybe at some point then we kind of do the update on the one and on the actor that's collecting the data. And then offline says, hey, we're not even going to go to collect the data, but I have a data set, so we're trying to do this as a supervised learning. And then there is also for kind of, if you dig into math and so on behind, there are reasons there are often separate algorithms for discrete actions and for continuous actions. But looking into how is reinforcement learning fundamentally different from supervised learning, there are three areas. First off, we have this closed loop training and evaluation. We're going, collecting the data, right? And then we're training on that and so on. Second area is there is the POM-MDP formulation, which does not exist in supervised learning setting. And the third one is that the application domains are different. We have the autonomous systems, right, and so on, where these problems are applied. So when we look how they're fundamentally different, these three areas kind of need to keep in mind. So let's kind of look briefly into each one of these three. First off, this closed loop business of training, where we have a policy, we learn, then we go collect more data. And now we're back into collecting more data, training and so on. The implication is that every iteration on training changes the data set underneath our feet, right? So we have this auto distribution and non-stationary data set that we need to deal with. So some ways this is being dealt algorithmically. We have something that's called replay buffer that stores all the, well, not all, that stores some of the data that's being collected. And then the data that's being used for training is being subsampled from the replay buffer. And then we have these actors, that's maybe one of them, that we copy the policy to stabilize the training and so on. So there's a lot more complication algorithmically that's being introduced to deal with non-stationarity of the data in the algorithms. I want you to look at this video. This is a video of a robot performing the same task, going from one point to another point in the environment and kind of repeating that task. Now the path is blocked, so it needs to kind of adapt and go around it. The robot sees with its LiDAR, so it sees kind of where the obstacles are, and then produces velocity, linear and angular velocity. What strikes you about this video? Anybody? Wake up. Trial and error. Okay, so this is actually trained policy, but one thing that robot needs to be reactive, right? So the decision, it needs to react to kind of obstacles and so on that's going around. Second thing, safety is important, right? The training here, this robot is 120 kilos, going 5 kilometers per hour. You don't want it to hit it. This is, by the way, AutoRL policy running on it, trained using learning the rewards, but we'll go to that. So my point here was that the latency or the time that it takes to make a decision can make or break reinforcement learning systems on the evaluation side. So we're not learning at this point. The one kind of common wisdom is that, well, the bigger the model is better, the more capacity there is, that you can make better decisions, be smarter, and so on. But realistically, what happens is that the inference time grows. And as inference time grows, my situation, tactical situation, person can come in and collide with me if it takes me 2 minutes to come up with a decision. I'm going to the extreme here, but you kind of get a point, right? So the uncertainty around what the state of the environment grows exponentially at the same time. So as the model gets bigger, the certainty and safety decreases. So there is actually some sweet spot here. This is completely made up graph, but by the way, that doesn't mean anything. But there is some sweet spot there where bigger models are not always the better. And we're finding them experimentally, trial and error. And the next slide. Having issues with the slides. Okay, well, next one. So next area where was RL is different from supervised learning is this partially observable Markov decision formulation. And if you pay attention to the tuple that I said, it never mentions function approximators. It says we need to learn the policy. And in kind of good old days, back when this theory was kind of developed in 50s and 60s by Bellman, these were Markov decision processes. They were fully observable. All the states were known, and they were tabular, and there were small spaces, and used the dynamic programming, and you have your optimal solution. Nowadays, we're dealing with partially observable Markov decision processes, large spaces, continuous spaces, and so on. And function approximation is the way to go. And there is really no theoretical framework how to deal with the function approximators. And we see them as a policies, as an actors, right, in a whole different places. And again, we're doing this experimentally. Back to manual. All right. The second area is that, again, I mentioned these are the systems. And the other thing that's not specified in the Markov decision process is the simulator or the transition function. Yeah, there is kind of given transition function, but not really physical space or the physical environment in the way that we mean. So what we ended up constructing and learning simulators that for real world applications can be very complicated. They contain hidden space. We don't know what that hidden state is. So there is, again, lots of trial and expertise needed to define good simulators that we can use for training. And then we need to put it in a real environment like we did on the robot there. And then we need to deal with what's called sim to real gap and hope for the best. And then again, based on the applications, safety and generalization come hand in hand because, again, if we're dealing with robotics and real systems and so on, we can't train them on the robots often. There's the hardware damage, there is the property damage, right? It's impractical in many cases. So inherently, we really need to worry about generalization. And again, that's being dealt algorithmically. Figure out the slides. All right, so back to the this diagram of three kind of pillars where they're different, is that we're dealing with a model latencies experimentally, function approximations experimentally, simulator design experimentally, and then inherently we need to care about distributional shift, safety, and generalization, and that is being dealt as algorithmic design to provide both training stability and generalization and uncertainty. And this is why we now have this graph with a whole bunch of algorithms and so on. This is why they're popping out as mushrooms. It's a hard problem. So what is really the reality then? We started with this diagram and kind of as we went, like now we're tuning the algorithm and kind of learning the neural networks and so on and trying different things there. We're tuning the rewards and whatnot. We're tuning the simulator and the environments and so on. So here is your favorite applied reinforcement learning engineer or researcher or whatnot, basically in the loop, observing the performance of the system, checking out how it performs, what's the state and how it performs, and decides what next thing to tune and so on. This is sequential decision-making problem, which means we can probably apply RL. But this is kind of how it's been largely done nowadays in the normal thing. Fun fact, this icon is created by DALL-E. So I mentioned there are these 4 areas that we are optimizing for and trying to tune. So the premise is that we replace human or manual process with a learned model or automation. And so what we're doing then, essentially all these kind of undefined things become a new parameter zeta in our optimization problem. And we're looking to maximize the zeta, find the zeta that improves the performance of the reinforcement learning agent. And slightly more cleaner and optimized, the AutoRL problem formulation here, as we kind of understand it, is it's a really 2-loop or bi-level optimization problem, where in the inner loop, so all this stuff that we're trying to tune is encoded in the zeta, and first loop, the inner loop, is trying to find policy or the parameterization that maximizes the return with a fixed zeta. And then we fix theta and optimize or try to find the zeta that maximizes that performance of the reinforcement learning agent of the inner loop. That's the rough idea. Okay, so in terms of the hyperparameters, and there's going to be a little bit of the naming overload here, so bear with me. We're going to consider everything a hyperparameter that we talked about. So everything that's kind of encoded in the zeta is the hyperparameter. It can be categorical, it can be a vector, it can be symbolic, or parameterized function. So symbolic means we're kind of giving a program and so on. The parameterized function for all purposes are nets, neural nets, but they don't have to be. Or can be combination of them. So these 2, categorical and vector, we often call learning hyperparameters, and these would be things like learning rate, gamma, find the discount factor, all your kind of favorite things that there's a little parameter here and there and so on. And let's kind of say they're a low parameter regime. And then we fairly understand the left side well, and the right side is the high parameter regime, where it's really like we're looking at the algorithm, we're looking at the program, we're looking at the large neural net, right, and so on, replacing rules and so on. And this is where lots of open research is heading. Second way to look at the, oh yeah, so I should mention here, one thing that we don't understand is really the codependencies between the algorithms. So this is, I think, one of the huge open areas, how they depend on each other and so on. So the other way to look at the hyperparameter taxonomy is by training step dependence. Are they stationary or they're non-stationary? So in other words, if I train my reinforcement learning agent, is there one value of that parameter that's a constant for the duration, or does it need to change with the context of training? And here is an example, just kind of as illustrative, that if this function that we're optimizing, this hyperparameter, this is what function looks in step 1, step, 1,000, step 10,000. So which parameter is better here, right? So for largely we're we're treating hyperparameters as being stationary. How good that is or how good that assumption is, we don't know quite yet. So hyperparameters stationary, we know that seed and discount factor generally tend to be stationary. The non-stationary, we know that learning rate should not be stationary, exploration rate should not be stationary, actually it's not. But then for the rest of them, such as neural network architecture, discount factor, reply buffer size, the sampling policy, loss functions, and so on, we really don't know. So now let's talk about the cost for the AutoRL. This is from OpenAI stable baselines. Soft actor critic, but pick any other, has 28 hyperparameters to specify, just out of the bat. Right, and now let's add that we really need to kind of figure out the algorithm and the neural network architecture and so on. And this outer loop search space becomes really big, much, much bigger than the AutoML, right? On the other hand, let's not forget the inner loop. The RL training, or what's the evaluation of the AutoML, takes a while. It often takes millions of samples. Atari games are often trained on million samples. Depending what you're training on, it can take a day or two to complete a single run, even a week. Like if you're doing Atari on 100 million without further optimization. So this is very expensive as well. And we pretty much have a multiplicative effect here, right? So what do we do, right? We simplify the top part and just kind of look at the several hyperparameters at a time, or we simplify this and train on simple problems, right? That can train in a couple of minutes, and then it allows you to do many iterations up top, but then are you solving really the difficult problem and the right problem? And this is a big question, right? So generally approach that has been taken is that a little bit of both, that there are kind of pieces or chunks, distinct chunks that we're learning here, but then we're also compromising on what applications we're using to evaluate. Okay, so to summarize the AutoRL considerations, we're consider here hyperparameters, everything that's not specified in POM-MDP. And these hyperparameters can be categorical, symbolic, continuous, can be stationary or non-stationary, and we need to understand their codependencies. And then we really need to be careful on the design. What we're doing here for the evaluations in the outer loop is that to control the size of the search space and how long the evaluations are. So next I'm gonna go very briefly into what the training methods are, and you guys should know this already, but it's a good time to stop and ask if there are any questions right now. Take a breath, stand up. All right, so training methods, these are all your favorites that we're using in the AutoML. But one thing, oh, it's working, haha. The one thing that I do want to mention, because I see it all the time, it's kind of one of the things that's my pet peeve, is when we're doing, don't do grid search. When you're doing more than the hyperparameter search for in more than one dimension, the grid world kind of gives you a lot. It just gives you partial information on each dimension. Random search, like if you're not going to even do learning or anything, the random gives you a lot more information just to pick the maximum in each dimension. So that's there. The reason I'm saying, like, if you look at the stable baselines or so on, or in many packages, is default by grid search. You're wasting computational resources. Okay, so second, a lot popular method, the evolutionary methods, generally starts with some kind of population that's initialized. Then there is some kind of method to select survivors to reduce the population. And then we can change the population based on either mutation. So we pick one or some members of the population, we change them a little bit, or we recombine them. So take several of them and combine them together. And then we continue with the new population, kind of keep that circle going. Very popular across the board, handles both differential and non-differential or situations. Multi-arm bandits, it's a simplified version of sequential decision-making process, also very popular. It basically selects actions, but without having to deal with the states. And there is kind of a little diagram here where bandits are, what is MDP and where is RL kind of lives in this role. RL would be a good tool to learn for the AutoRL is a learning method, but we're talking about how this is complex and it's going to be way more complex to do it. Bayesian optimization, also very popular, generally works in 3 steps. We have some data, we fit a Gaussian process or regressor through it that kind of gives the uncertainty estimates. Then we create acquisition function that kind of creates this exploration trade-off. And then the argmax of that acquisition function is the next sample that it recommends to do. Also popular, especially in reinforcement learning, is the MAML or meta training multitask for multitask learning. The idea is that we learn a meta gradient here on the distribution of the tasks. And then when we're given a task, we can do a fine tuning with just a few samples in one direction. And this is, I think Chelsea is giving the talk today. She's the expert. And then I want to also mention population-based methods for training, which I'm personally very excited about. These methods do both stationary and non-stationary evaluations at the same time when we have a population of agents, and then every once in a while during the loops, they exchange the information and so on. And I know lots of you here work in this area. Any questions here? Yeah. So now let's talk about what to learn. I will mention here, there are roughly 4 areas of the things that we tend to do today. The one is the reinforcement learning components. So this would be your learning hyperparameters, your neural network architecture, and generally the algorithm design. The second one is the rewards. And we'll talk about why rewards are important and so on. And then last one is the agent, so observations and actions, things that kind of, how do you design the agent? And the last one is the environment. And they're kind of in this area because these are more established and then going to more cutting edge research and so on. So the first, we're going to start with the hyperparameter. These are the learning hyperparameters that we know how to do and so on. So our focus Richard is going to talk about the tools that are available, how to do it, so something practical, and then go into neural network architecture afterwards.
Cool. Yeah, so in order to talk about hyperparameter tuning, there are 3 main different packages out there. And also talk about the comparisons between those packages. So the first type are services. They host algorithms on a server and also include our very own open source Vizier, but also include things like OpenBox. They're generally more flexible and scalable, but at the cost of additional engineering complexity. The second one are frameworks. So they execute the entire optimization themselves. And while they're convenient and automate everything, they also require knowledge of the entire evaluation pipeline, right? So these include Axe and HP Banster. The last one are libraries, where they just implement black box optimization algorithms and say, okay, you can do whatever you want with them. They offer the most freedom, but they usually lack scalability features and are limited to only one machine. So these include PyGlove, which is for evolutionary algorithms, and also BioTorch. Yeah, so shameless advertisement. We have open source Vizier. This is an open source version of the Google's internal service. Its core method is basically black box optimization, and it is made to scale for a large number of clients or not large number of like evaluations, right? So it allows distributed multi-client and reliable tuning and supports most types of black box optimization. Here's the link, by the way. Does this work? Yeah. But yeah, this is how normally people do AutoML for the black box optimization case at Google. And so for reinforcement learning, what you can do is, this is a pretty simple way to just do evaluation over, let's say, a regular AutoRL training. So this is using the dopamine framework. And basically, it goes in 3 sections, right? The first section is basically you define the evaluator. And also this defines basically also the search space. And you might define, okay, what algorithm do you want to use? And the second part, basically you define like the client, as in how you're going to communicate with the server. And the last part is basically the evaluation loop, where you're trying to get the suggestions from the server, evaluate the suggestions. That takes the most amount of time, and then you report back your measurements. Yeah. So then moving on. So the first part I want to talk about what we want to learn in our AutoRL, our neural network architectures. So why does that even matter in RL, right? We know why they matter in supervised learning, but it turns out it also really matters in reinforcement learning. So architectures matter for, let's say, inference speed, right? If you're running this kind of robot, which takes like milliseconds to make an action, then you really need a small policy. And sometimes even like a fully connected neural network isn't going to cut it. It's way too slow. Another case is generalization, where recent work such as the ProcGen benchmark showed that the architecture really matters for generalization. They showed that, for example, like a residual network does a lot better than your default DQN network in terms of generalization. Another one, of course, is sample complexity, right? If you train like in images with like an MLP, that's going to be way slower than you training it with a convolutional neural network, right? And another one is adaptation, where you might be able to, let's say, find a better RNN for doing meta learning, let's say. This is on the meta world benchmark, where you're supposed to adapt to new tasks. Yeah. One thing is that you want an efficient method for NAS and RL, right? The original trial by trial formulation, that's way too slow. For example, CFAR10 already takes 2,000 plus GPU days, right? You can only really do that at Google or like any other industry for neural architecture search. But in RL, the noisy evaluation from all this like learning curves only makes it worse, right? Sometimes when you train an RL agent, it completely fails, but that's not because your algorithm or method is bad. It's just you're completely unlucky. Yeah, so you don't want to burn lots and lots of cash. So the question is, what are some efficient methods? So the first organization is basically, let's start out with low parameter regimes. So, right. So these are basically at most like 10K weights in your neural network. And they're more about like mobile robots or, environments such as the Carpool and Majoko, right? Most of these methods currently optimize the architecture and weights simultaneously. And they just treat it as like one single search space. So for example, like evolutionary methods such as NEAT, that's pretty long ago. Or like you can apply directly other evolutionary techniques more recent, like regularized evolution. We have one work that tries to optimize both directly using some of the most well-known evolutionary methods. And usually your networks look like this, right? Where basically there are only a few parameters and they might look pretty combinatorial. And these nodes only represent like a single floating point number, right? So yeah, these are both like classic and also newer evolutionary methods. The caveat here is that such methods are zero order and they suffer under way too many weight parameters, right? So in standard deep learning, use almost like 1 million weights, right? That's even like the most basic, smallest network that people use for RL, right? And so then that changes where you might need to use gradients for weight training. So one method we found actually is darts works pretty well in actually RL. So the reason is because it's very minimally invasive, right? In reinforcement learning, when you train a policy, you can actually have many different distributed components, and they're all communicating with each other through like some, RPCs or something. And you don't want to complicate the process too much because it's already kind of complicated. So in darts, what you can just do is replace your network with the supernet. Hopefully, some of you are aware of the NAS supernet, one-shot network, that kind of terminology. And it turns out that this actually works pretty well. For example, this is a cell we found for all ProcGen games on, I think, DQN, and it works pretty well. Like it got maybe like over 200% improvement on certain environments. And it's really simple, right? You just disable your original network and plug in the new supernet. Yeah. As for other methods in the high parameter regime, it's actually kind of an open question, right? So there's actually pretty little work so far in the high parameter regime, right? So in black box optimization, the core issue, as I said earlier, is how do you deal with the very strong noise where even one trial can be catastrophic and that might fool your optimizer, right? We don't know if like evolution might work in that regime, who knows? I think there's one paper that does something Bayesian presented at the AutoML conference, but it's still maybe unclear, right? Other weight sharing methods, right, like ENAS, use basically what's called a controller to do weight sharing. The issue there is that like it's kind of unclear how you should put it in your distributed pipeline, right? So the issue is like how do you make it simple, right? And there are a few others that are also, I guess, more classic, right? I think HyperNeat still somewhat treats as a black box optimization case, but how do you scale that to modern deep learning is unclear. Yeah. And let me give this to Yingjie. Okay.
Thanks. All right. So next area on the kind of algorithmic side, on the agent side, is the learning loss functions. And the main idea is that the loss function itself is a parameterized object. We lost that. Okay, there is. So we can kind of divide these methods for learning loss functions in neural loss, where the loss function is represented as a neural network, or symbolic languages. And then in terms of learning, the neural losses, we can do evolutionary or gradient descent methods. And then on the symbolic, we either do selection and search or domain-specific languages. The one thing that I should mention is that the search space can be very, very large. So Gray and Lewis paper, it's on archives. We're looking at vector-critic policies that are stable for training, perform well, and generalize. And the space of parameters is at the order of 10 to the 100. So we need to be really careful about design, pruning, and optimization in these methods. And generalization is the key because that kind of brings the economics of the methods. Okay, so on the neural networks, losses and neural networks with evolutionary methods. Again, this is not intended to be inclusive. There is work, but kind of one of the works that is representative is that the loss function is represented, and they come up with the architecture that creates these temporal convolutions where we kind of see the history of agents' actions and then do convolutions on top of that, and we learn the policy. These tricks of kind of doing several lost observations when training the RL agents is something that RL community and applied RL community does as kind of best practices because it gives you a little bit of the history. What they're doing that, they're basically putting that into architecture for the loss function officially, and the loss function then becomes adaptive to the environment and the agent history. And they end up with a faster training and generalization to out of distribution data across different Mujako environments. So if it's trained on ant, it goes on the humanoid and so on. The second area is basically, again, the loss function is neural network, and we're using people are using the gradient descent in this space. So two examples. One is the MetaGen RL, which is really neat. It uses population of agents. Everybody is exploring, can be working in different environment. It can be basically collecting the data, and all that data goes to the to learn the policy, and effectively each of the agents learns the part of the subspace of the loss function. And then another example is the learn policy gradient. In this case, they were using the LSTM to do a similar thing. And these methods do require Jacobian vector product compilation, which like take any package X, Torch, or TensorFlow, it's readily available. And all of them do some domain, cross-domain generalization. So this one, I believe, goes from toy environments to Atari games and so on. So this is promising. This is kind of where we want to get to, the really cross-domain generalization. Last area is, so on the search function, it's very simple. There's very little work. So there's one example work. But on the symbolic function, the idea here is that basically your loss function is a program. And nice thing about that is then it's fully interpretable. It's a program. It's a computational graph. And it's fully interpretable, which means that A, we can use standard tools for the analysis of the algorithms and so on. We can also have people work alongside with so if I don't like this, I can tweak it here and so on. I can put it back in the population and so on. So two examples of this work is that one is learning curiosity module, and search space combines actually different parts of the algorithm. So neural nets, buffers, and custom losses and so on. The other work is loss function is a directed acrylic graph. And there's lots of tricks due to the size of the space. So Yingje is going to talk and kind of walk through the code on what that looks like and what are some of the trade-offs. But one thing that's really interesting is, again, they're interpretable. And this is the first time now that we have thousands of algorithms and their performance that we can go and sit and analyze and so on. So if somebody's kind of theoretically minded and so on, they're there. Go and kind of look at them and see what they're doing. What's interesting is that they map to very few specific areas. So even though we have thousands of algorithms, they're very kind of discretely spaced out, and I don't know why. But now for next, Yingje is going to do a deep dive on learning loss functions.
Thanks, Sandra. So, okay, so how are we going to meta-learn algorithms? So the idea is that we can treat RL algorithms themselves as points in a hyperparameter space. And then to discover these new algorithms just means we need to do hyperparameter tuning in that space. And with this view, Correas et al. Discovered that new value-based RL algorithms that outperform baselines. And importantly, these algorithms, they are interpretable by humans, and they are transferable to new environments, and also they are implementable. So in this tutorial, I will first go over the algorithm representation and the search space design for this search space. Then I will discuss the optimization methods and some of the tricks we used. And in the end, I will show some high-level code examples. All right. All right, so as Sandra mentioned, we can view this RL algorithm and their loss function as a directed acyclic graph. And you can think that this graph can be built incrementally, one node at a time in topological ordering. So here we are using DQN, a classic reinforcement learning algorithm as an example. So now how can we turn this into a hyperparameter that can be optimized? So with topological ordering, each DAG can be viewed as a sequence of categorical hyperparameters. So there is no magic here. So we have one one categorical hyperparameter for each intermediate node and the output node here. And more specifically, for the intermediate node, we are concerned with which op can we use for that op, right? And for an op we choose, what are the previous nodes we can use as the input? And for the output node, we are concerned with which of the intermediate node we can use as the output. And there will be some encoding and logic needed for mapping between these abstract hyperparameters to concrete DAGs. As you can see, the meaty part of the search, the meaty part of the search space coming from these intermediate nodes. So now let's look at them in detail. So here we list all the operations we have considered. And some of these are very straightforward tensor operations, such as add, subtraction. And some of these are neural network operations. They basically map states to some Q values. And some of these are somewhat special for reinforcement learning algorithms, such as a select list. This is used for given a list of Q values of the actions and the action index. Then how do we select into that list? So these operations cover many known value-based RL algorithms, and these operations has typed inputs and output. So that really helps to prune the search space. And in practice, you also want to put some a cap on the size of the graph. In practice, we found around 20 worked pretty well. So now this completes the specification of your hyperparameter search space. Next, you are going to define an objective function, and then you can just plug in your favorite hyperparameter tuning algorithm to discover algorithms. All right, so here is a end-to-end picture for how we can optimize over such complex search space. Here we are using regularized evolution as an example. On the left, you have a pool of population of these DAGs. The population is initialized. It can be randomly initialized, and optionally, you can augment it with some known algorithms. So that helps the search to warm start. And in the middle, the evolution algorithm is responsible for proposing new candidates by running tournament selection and the mutations. So once an algorithm is proposed, then we are going to run this algorithm on a set of meta training environments. And the optimization objective is the sum of this normalized return on this set of environments. And once it's trained, then this the score is feedback into the algorithm. So as you can imagine, this process repeats many times until we swept over a large number of candidates. So this can take a lot of time, and distributed training is paramount. So in the paper, we used the 300 CPUs for 3 days, which swept over 20K candidates. In addition, we used several speed-up tricks. The first one is a hurdle environment. We use Carpal as a hurdle environment. This is for fading fast. If some algorithm cannot do reasonably well on Carpal, then we just skip the harder environments. And the second trick is this so-called functional equivalence hashing and caching. This is for deduping the same candidates. So what do we mean by functional equivalence exactly? For example, as the computation graphs, x plus x is different from 2x, but they are algebraically equivalent. So functional equivalence really means this algebraic equivalence. However, determining algebraic equivalence for such complex graph is highly non-trivial. So what we use numerical as a proxy. So we have a set of fixed inputs. These are random inputs, and then we just run this DAG on those inputs, and then we hash the results. So once we detect something is a duplication, then we just read the score from the cache. So that saves a lot of computation time. So here we highlight one of the discovered algorithms by this evolution process. This algorithm, we name it as DQ and reg because it's just a standard DQ and algorithm plus a regularization term on the Q values. And by some analysis, we can show that this regularization term here helps the agent to do more exploration, which is very critical for some reinforcement learning algorithms, for some reinforcement learning problems. And we show that DQ and reg, although it is trained on some simple environments, it generalized to a lot of different environments. For example, it does even pretty well on Atari games, even though it's not trained on any of these image environments. Next, let's change gear and look at some code examples. So we open sourced this code recently. These are a single processed version of the distributed training code we had internally. So the code is built on top of two awesome libraries. One is PyGlove from Group Brain. This is very recently released. And the other is Acme from DeepMind. It's an IR library. So first, we are going to define our search space. So recall that our search space are these DAGs of a fixed length, and you have many choices for each node in that DAG. And this idea translates very naturally into this PyGlove construct. So you want to have a list of things, and for each item in that list, it could be one of many possibilities. And we emphasize that this hyperparameter here is not an ordinary primitive hyperparameter like floats, strings, or integers. This can be arbitrarily complex objects. And what PyGlove does very good is, you can express high-level complexity of your search space, but then it handles the encoding and the decoding of the hyperparameter and your objects. And second, you want to define your search algorithm. Here we are showing an example of regularized evolution. You can build this regularized evolution algorithm in a few lines in PyGlove primitives. And in fact, PyGlove itself comes with many built-in algorithms, such as some are RL-based, like reinforce or PPO. And I believe PyGlove comes with a regularized evolution built-in. Yeah, this is more like an example. Okay, now we are ready to define our main training loop. The main construct here is this pyglove.sample. This nice syntax just says, I want to sample from this search space using my controller algorithm. Here is the regularized evolution. And in the loop body, you are going to have one sample. This is the hyperparameter already decoded. So it's ready to be evaluated using your objective function. And once it's done, all the evaluation results can go into this feedback object. And on the right, we're showing a toy training curve here. It's trained on multiple environment for 100 trials. It's very tiny. This can be done on a single CPU for maybe like 1 hour-ish. And you can see that the algorithm already picked up some signals so that towards the end, it began to sample high fitness candidates more often. Yeah, so the end-to-end collab is available here. All right, now I'm handing this to Sandra.
Thank you, Yingje. All right, so back to summarize on the loss function, the different methods. Careful design, pruning, and optimization are paramount, but what's exciting is really that they're starting to generalize across the domains. We know that policy gradients and actor critics are more challenging, and the open work is really kind of looking at the whole algorithm and not only at the loss function. So next, let's talk about rewards. So rewards in reinforcement learning specify the task. It's the only mechanism that the agent has to or that the designer has to provide to the agent to tell it what it wants. And if you look at if you consider what is classically done, or kind of what the theory says, okay, the reward should be sparse and you can just reward the agent once it reaches the destination and completes the task. This is what's known as a sparse task. What that kind of leads the agent is it's non-tractable, right? There's so much exploration that needs to happen and so on. Very simple example here. We're giving tutorial here. We want you to learn something and be successful. There are two ways to do this, right? I can give a tutorial and then take a survey and say, yeah, we did that, and tell me, yeah, that wasn't useful, right? And then to try to do this again and again. That's the sparse reward. Or I can do what's called intrinsic reward, kind of look for the signals along here. It's like, how many of you are snoozing? And how many of you are actually taking pictures or so on, or smiling, right? And that gives me a feedback, what I call intrinsic reward. Like, yeah, I'm doing well or I'm not doing well. Nobody's taking a nap. And then just as an example here, let's see. Okay, so remember that first video of the robot that was kind of going through the micro kitchen? This is the same thing, just differently parameterized reward. So that's what a reward does. It's still getting to where it needs to go, but it's really not optimal, nor ideal, kind of keeps looping and circling. So what do we do typically? There are several methods that all either, there's the extract rewards, what is that we want the robot to do, go complete the task, and then we're either learning a surrogate reward, like the feature-based rewards and so on, or we're adding different reward functions. There's tons of literature on kind of encouraging agent to do certain thing by adding a term to the reward function. So this is kind of the left part and so on. The feature-based methods tend to go and say, hey, we do have some knowledge of the features of the reward, such as whether who is snoozing and who is taking pictures type of thing. So we can use that, but we don't know how they relate to each other. So let's parameterize it and so on. And we'll do kind of deeper dive into the Cheng and 19. Fun fact, that was the first paper that used the AutoRL. And that term was coined by Louis Cheng, the first author on the paper, was my intern at the time. And that was the robot video. And my clicker is not clicking. I know what's going on. All right. No? Okay. So reward shaping helps for more complex tasks. That's basically, and what we're finding out that actually the exact method is less important, how we actually do it. All right. So this was the first paper on kind of learning the rewards. The idea was, and this was the task of kind of having the robot go from A to B, dealing with whatever obstacles and getting to the destination. The extracting reward there is get to destination. I don't care how. However, we do have good features that we can kind of think of what's important there, like what's the distance to the goal, what's the distance to the nearest obstacle, right, and so on, that we can kind of get out of the sensor information, but how they play together, it's not clear. So that's the intrinsic reward, that's parameterized features. And we start with a population of agent, and everybody kind of gets randomly initialized reward. We train them, we evaluate them against the task objective, which is whether you got there or didn't get there. We do a mutator. In this case, we use the Bayesian optimization. In this case, it was evolutionary search. Get the new recommendation for the next reward, spend the new agent, and so on. It was actually used training with Vizier that Richard was talking about. And at the end of the day, we have the policy and we use that policy and so on. In reality, we did a second loop here doing the neural network architecture search after that fits the neural network architecture into the reward. So we're looking at the layers, the depth and the width of the layers. It did improve the performance, but the reward here was much stronger signal. It's not cheap. So single trial training that was taking about 12 hours at the time to 24, and it was the equivalent of the experience that it was million samples or so on. So equivalent of 12 days of training in kind of real time if it was going to do it. But then in order to get the reward, it's 1,000 trials, which is the experience of 32 years. So not cheap. And was taking 5 days to train. All right. So this is the simulation environment that we're using for training. And after it's trained, you can kind of plop it on the robot and runs. And turned out it runs on kind of many different modalities, kinodynamic robots with the kinodynamic constraints and so on. And then after that, I was like, okay, where else does this work? Is it just the robotics or is it so on? So we kind of did a larger benchmarking study across different Mujako environments and different reinforcement learning algorithms. And some takeaways there is that if it's a complex task, use the reward shaping. So on this is difference on the humanoid, it's huge. On ant, there's like hardly any difference, or the bipedal walking. The second takeaway is if we start with the good hyperparameters that are basically known and so on, reward shaping is more likely to give you the better performance sooner. So as long as your learning hyperparameters are good enough and you have complex tasks, go with the reward shaping. Third, which kind of in retrospect wasn't surprising, but it was at the time, that there is a codependency between reinforcement learning algorithm that we're using. So for example, soft atrophy and PPO ended up in different parameterizations and intrinsic reward. And we took, like, if you're familiar with the Mujako environments for folks that work in the RL, that reward already kind of has three features, right? With kind of fixed parameters. If we basically just went intrinsic rewards is reparameterization of that, depending on the algorithm that we're using, it could work, one works better for PPO, the other one for soft actor critic, and so on. And basically what we're hypothesizing that intrinsic reward helps shape the landscape of the learning loss function and kind of helps it learn faster. And then third one is we want to know, okay, if I don't have a reward and I'm kind of in the applied setting, should I spend my time engineering the reward like in Mujako? Or should I just do a simple, because this Mujako task is like fastest, maximize the speed or maximize the like distance run and so on. So the gap of the performance between using fancy hand designed rewards is minuscule. So if you don't have a reward, go for the extractive, being very simple. You got to the goal, you didn't maximize this, and then use the features that you have at the disposal and let the learning kind of handle it. So that's on the rewards. Next, I'm just going to go briefly. Let's see on time. Yeah, work it. We start a bit later. Environment-based learning. This is kind of more of the frontier now. Roughly, we can learn the action space. We can learn observations and the dynamics. On the action space, people have looked at hey, how we simplify the actions and kind of reducing the blowing out of the dimensionality. So can I learn both what action to take and for how long? So go straight, but like 20 steps if I'm gonna exit here, or how I can combine them into more of the macro functions. On the observation space, work that has been trying to do, well, there's been using the image perturbations to augment the data that's kind of being sent for more robust and policies and generalize. And last, in dynamics, I know it's not technically AutoRL and learning to learn, but we're models in learning the dynamics of the system from the observations and so on is very promising direction with kind of reduces lots of hand design that's going on. Next area that's kind of emerging that I'm very excited about is designing the environments and design the curriculum. So the question here is, we need to have just the right challenge for the agent to do. So if we put too complicated tasks and so on, agent's not gonna do well. So we need to kind of, and there is lots of like hand design curriculum and so on. But this new set of methods is looking at, given what the agent knows and how well it performs, how can I design the task and the environment that just the right challenge and kind of keeps growing that and making harder and so on. And it improves generalization. It's very sensitive to tasks. I don't know it says learning methods as well, but tasks as well. And there's lots of current work in this space. One thing that's very interesting is we're talking about new algorithms, right, and hyperparameters and so on, and that improves the agent. This does not touch the agent. The only thing it changes is the data that's being provided to the agent to learn. So in a sense, you can kind of look at the algorithmic and reward, intrinsic reward as nature of the agent, and the data and stuff that's being fed to it is nurture. And how these two play together, what's data being given to the system that you have in hand, it's a very interesting trade-off that I think we should kind of look more into. And then just kind of want to bring your attention on methods that do combination of these things. So we're kind of looking, okay, there are the algorithmic parts, right? And there are the rewards and whatnot. But there are some methods that combine rewards, neural network architecture, and learning hyperparameters at the same time. For the RNA design, with a very promising results. There's also work on looking at co-design of neural network architectures and the accelerators. And generally, the idea in this space is that oftentimes, well, we train these models and they're becoming bigger and so on. We're training them on GPUs and so on. And then you put them on a little quadrotor that has a tiny little chip, and the policy is completely different, right? So we need to ask ourselves what the target system is and design the neural network for that system, or given a neural network, how we can get the best out of the compute that we have. So there's like a whole line of work in this space, and using Bayesian optimization and other methods to automate that process is leading to 2x performance. All right, so what's a summary in these learning methods? What do we know, and what do we not know? I feel this should be like a trivia now, but okay, that's fine. So we know that if you have the learning hyperparameters, do learn them. If you're not gonna learn them, please do random search and not the grid, promise me. Second, if you have decent hyperparameters and you have complex enough tasks, do shape the rewards, learn the rewards. And the third, curriculum produces really strong results for generalization and learning increased difficulty. It's sensitive to tasks, but keep that in mind. Loss functions learning has very promising results in generalization. There is more work that needs to be done on how to expand just from the loss function to the entire algorithm and so on. Things that we don't know. Richard mentioned there's, and I know some of you work in this space, there's little work on INAS. Some of the work that we had, basically it seems like the rewards and so on seem to be bigger problem du jour for reinforcement learning community, and NAS has been kind of neglected. Hopefully that's gonna change. There's very little working in this agent learning and design, because that community, these work is kind of happening in the applied communities, and there isn't that many communication and kind of lessons shared between different applied communities. I think that like the whole area can be really accelerated with the automation. We don't understand what are important components to learn. Which one is more important? Should we look at the replay buffers? Should we look at the different actors and so on? So where are kind of the meaty problems, or not meaty, but the impactful problems, I should say. To this day, we still don't know which hyperparameters are non-stationary and how to learn them as non-stationary. We don't know how to learn many components well. How do we do curriculum with a neural network architecture search, for example? The reward and the loss function at the same time, and so on. And what are the best learning methods for component? So this is my take on kind of what the big open problems are. We need a lot of badly theoretical understanding on these hyperparameter codependencies, which methods are appropriate and when, and so on. It's a very experimental field. We need some kind of fundamental theoretical understanding there, because the whole theory of POM MDPs and so on, the way it is, it's largely non-applicable here. We do need practical benchmark. AutoRL does not have a benchmark, and we're making these trade-offs between, do we make the problem like the inner loop too simple, or do we make the outer loop, the AutoRL problem too simple, and so on. And we kind of keep going back and forth until something works out. So if anybody's interested in doing a benchmark or collaborating on the benchmark, please do let me know. The metrics come to mind as well. How long does it take to train? How long does it take to train the outer loop? What's the cost of collecting samples and everything else? Nature versus nature trade-off, I mentioned that how much data and curriculum and so on versus kind of changing the agent itself matters, and how do we do that together, which is kind of reason why I'm very excited about the population-based training. And then integrative methods. I touched on that. How do we do some multi-generational evolution where we're changing the agent in the process and they're learning from each other and so on, and kind of start tackling larger groups of hyperparameters and so on. All right, so 5 things that hopefully we got out of this. We understand why RL is so darn complex system to deal with, why there are so many more knobs and independencies, that the stability of training and stability of evaluation play a huge role. And that kind of changes how it's the approach to the field compared to the supervised learning. The auto distribution learning just came to the supervised community a few years ago. Reinforcement learning and robotics applied community has dealt that since that's fundamental too. We talk about the formulation of the AutoRL and what the cost is, that we have this multiplicative effect of 2 hard problems. We talked about the hyperparameter taxonomy and the stationarity and non-stationarity. And we covered different parts of the reinforcement learning system that we're learning. The hyperparameters, neural network architecture, loss functions, rewards, agent, and the environment components. And then we discussed the future areas, and we gave some tools and practical things that you can kind of go and look. And just to end on the fun note, remember the little toddler, 10 years of the AutoRL training, and this is from yesterday. So we can do this. I want to thank Yingjae and Richard and JD and Jack, who couldn't be here today. And we did release this survey, so you can go and look at more comprehensive coverage of the literature and so on. It's there. And last but not least, thank you.
Shadow.
Hey, thanks for the excellent overview. I really enjoyed the talk. So you talked a lot about learning different components of the reinforcement learning pipeline. But do you think it will be possible to even learn the algorithm itself, like, for example, rediscovering policy gradient or some off-policy reinforcement learning strategy from scratch, from primitive operations? And what would it take to get there?
Very good question. And you guys can hear, this microphone works as well? Okay. So when it gets to, I'm differentiating between the loss function and the whole algorithm. And what I mean by that, the loss function is, this is the loss function for the policy gradient and so on. And there has been work, there are promising results, it's doable now. It was lots of work. I'm looking at to get there and so on, it's feasible. When I mention algorithm and I meant to include the slide, but if you go and any reinforcement learning algorithm and see like the soft actor critic or any of these algorithms, it's like 2 pages of code, right? And there are things there like now sample out of the replay buffer this and then sample there and so on, and now do a copy of the policy, and this is how many agents. This is what I mean by the entire algorithm, right? And that's a lot more complex and so on. I'm hoping we can get there. I think we should. I don't think we can now.
Thanks.
One more question here.
Thanks for the great talk. Do you have some insight to share with others about the stability of the training that you mentioned? Because we also observe this instability, especially when we train it disentangled way. Thanks.
So reinforcement learning community, and if anybody kind of wants 2 cents to add, by all means do. Has been dealt with either copying, so DQN and double DQN. What happens is that, okay, so we don't change the policy as we're going. We're going to copy and have 2 policies, and then every once in a while, we're going to update the policy that goes and collects the data. That way, the data is kind of more stationary and so on. The soft actor kind of critic sort of handle it that way and so on. So doing this policy copying business is one area. Second larger area that's kind of, there is more emerging literature on that and evidence, is that when we're doing and shifting the distribution to get the stability of the training, we need to have just the right challenge. So it needs to go baby steps. If it's too different, kind of drop and that doesn't work out, right? So if we're kind of shifting a little bit and so on, things are working. So these are basically controlling the amount of change and basically doing the stability by freezing certain pieces and continuing learning. Sure.
Anyone else? Yeah.
So you mentioned several times, and you write it big here, that there is a huge computational cost that is due to doing the AutoML and then training the RL, and then, but it seems to me that one of the challenges, but also one of the big strengths of RL is that you do this online. So can you not, like, includes the hyperparameter tuning and all this automated machine learning apparatus inside your reinforcement learning loop, and learn your machine learning algorithm as you are running it
in the continual setting.
Yes.
So if you're asking me if we should, instead of kind of waiting for, we go and train the agent and then we kind of collect how well it does. And then we say, okay, now next time we're going to do spin off next generation and so on. That's expensive. Your question is, why do that? Why just don't change them on the go? So the reason is, yes, that's kind of absolutely where field is going. And the whole population-based training, there is effort on reincarnating RL. Now that basically says we should never, ever learn policy from scratch. Continual learning means that we have the agent in this open-ended session and we're kind of updating the results and so on. So the reason is more historic, is that the tools that are available for the AutoML, we're kind of assuming you do a full evaluation. And the reinforcement learning community is like, well, you train the entire agent. Now we're getting like, well, this is really getting expensive and we shouldn't be doing this. So how about we kind of go towards population and start changing?
Quick question. Lots of papers came out recently with external memory. I wonder if external memory is useful for AutoRL and their application like KNN search for using, so like to speed up processing.
For the outer loop or for the inner loop?
For any of the parts.
This is why I like that this multidisciplinary conferences, because I think that generally AutoRL community has been looking as a simple outer loop methods, but that's actually a very good idea, right? And then kind of scaling up the inner loop through the population and kind of almost crowdsourcing it, doing like a large model outer loop training. Let's talk.
Anyone else? You mentioned nature versus nurture. Somebody? Yeah. Okay. Sorry. Okay, so you mentioned nature versus nurture. So how big is the effect you think of embodiments in these things? Because humans seem to learn faster, and we obviously have the benefit of eons of evolution and so on. So I was wondering, is AutoRL easier if you work in an embodied environment where you have more feedback on what the shape of the agent should be or what the rewards are?
Things are complicated. I think it's easier in a sense that your problem is better defined, right? So you have the system that you're given, so it reduces your design space largely. That said, on the other hand, it's really complicated to train them. You're dealing with a sim to real gap. You can't do it. There are safety issues, right? And a whole bunch of issues that go from there. Second, when and that's the reason I did this little gimmick with my daughter, like when we start walking, we're little and our center of gravity is low because we fall down a lot, right? And without hurting ourselves. And if you get a full grown adult, right, to start walking, that's we're talking physical therapy, right? So embodiment changes in biological systems for a reason.
Great. Do we have one last question? Who was first?
There were two questions, one in the back and one in the middle.
I don't want to steal anyone's question if they have it, so I could skip mine otherwise, but okay, I'll go for it. So, there's a lot of talk about the costs, especially at inference time, right? Basically, if you have more latency, if it takes you a second to make a decision, you've already crashed, right? And so in the space of supervised learning AutoML, ensembles are very dominant, right? But they have an inference time cost. And so I'm wondering, One, do you think that ensembles have a place in AutoRL? And two, do you think that model distillation has a place in AutoRL?
Yes and yes. So in terms of the assembles, there are people and there are methods that are using them during the training to find the better policies. So let's kind of train a bunch of them differently, initialized and then summarize them at the end, which kind of coincidentally says some of the recent research in the supervised learning community that says that in order to get robustness and so on from the fine-tuned model, you kind of fine-tune them with a separate the model soup paper I'm referring to. So that's kind of interesting. And this work on ReRL has been done before. There was this theoretical finding and so on. Your second part of the question was?
Around model distillation. So
Model
for example,
distillation,
like oftentimes in supervised learning, you can distill an ensemble into a singular model that would be stronger than if you just train that single model alone.
So that hasn't been done much, because historically reinforcement learning models have not been large. I mean, it really went in, robotics got very far with very little architecture, couple of layers of the neural net. Maybe we add a couple of CNN layers, maybe we don't, and that's about it. So there was not much need. We did, a few years back, we did experiment with distillation policies. There were some mixed results. But it's definitely something to look into, especially if we're going to go in this direction of kind of models ballooning in size and kind of being more general, then it makes complete sense to do that. And I think this is really kind of the larger point, is that these two fields have been kind of going in parallel, doing a parallel play. Now it's time to actually start talking and doing lessons learned between the two.
Gotcha. Thank you so much.
Sure. Okay. Just one last question. Go ahead.
Yeah, so Alex in the keynote this morning talked about how AutoGluon is down to sort of 3 lines of code, something that, a high schooler who knows Python could implement, right? I'm just wondering, I mean, is there, what might be a comparable win in AutoRL, right, where it could be accessible? Could we get to a point where, a high schooler or an undergraduate could do this as, a class project?
I don't think that you are that far off. I think as these fields go, there is always the cutting edge research that things complicated. That's what we do as a researchers, right? But then it's also worthwhile, okay, where is kind of the stops that we can make these things easy and accessible? So I think in that sense, some of the Acme and the stable baselines from OpenAI and so on, in terms of going off and starting to train reinforcement learning with whatever is there, Ataris, Mojako environments, and so on, a high schooler can do this. I have my own high schooler doing it. The TF agents, also open source library from Google has, and now with the Vizier getting out there, open source and so on, you literally can start doing that in a couple of lines of code, doing the hyperparameter optimization very, very easily and so on. So that can happen now at the level of the learning parameter. The hyperparameter for kind of more complicated algorithms and so on, well, that's kind of, we have our work cut out to do in that, to work in that space. Not quite yet.
With that, let's close and let's give Aleksandra one more round of applause.
And Ying J and Richard.
Oh, sorry, and Richard. Congratulations.